Hi, I'm Robin Ryder from Université Paris-Dauphine, and I'd like to thank the organizers of this virtual MCQMC conference. I'm going to be talking about a piece of work which is joined with three colleagues from Dauphine as well. So first we have Grégoire Clarté, who's a second year PhD student. He did most of the hard work on this project, and he's also presenting another piece of work in this MCQMC conference called Collective Monte Carlo. So you should also go check his talk out. And the other two co-authors are Christian Robert and Julien Ster. I'll be talking about component-wise approximate Bayesian computation, which is a class of algorithms we've developed where we are looking at interactable models and in reasonably big dimension, so that traditional ABC methods won't be practical in such a setting. Now, the idea here is inspired by the Gibbs sampler, so we're also going to call this algorithm ABC Gibbs, and the idea is therefore to look at ABC approximations of the conditional distributions, so considering each parameter conditional on the others. This way we'll be able to tackle problems of reasonably high dimension. Now, our setting is a Bayesian framework where we have a positive distribution, power of theta given x, so our data are x, and we have some integrals that we want to estimate by Monte Carlo. This requires getting a sample from the posterior distribution, and the class of problems we are interested in today are problems where this posterior distribution, power of theta given x, it cannot be computed, not even up to a constant, and it cannot be sampled from. So if we can't sample from it directly, that rules out Monte Carlo. If we can't compute its value, then that rules out MCMC a la Metropolis Hastings and so on. And we're also going to look at issues of the space of theta being of dimension d, which is medium to high, in which case traditional approximate Bayesian computation methods won't be available. Now, the traditional solution to untractable models is to use ABC. Now, if you don't know about ABC, here's a quick introduction. The idea is to simulate a value theta from the prior, and then given that value theta, we're going to generate some pseudo data, x, given the parameter theta, and this pseudo data, which we generated, we're going to compare it to the observed data. Now, if the pseudo data and the observed data are close in some sense, then we're going to accept theta. Otherwise, we reject and we repeat. Here, close is going to be defined by a summary statistic, S, some distance d, and a threshold epsilon. Now, ideally, if you have S, which is a sufficient statistic, and epsilon, which is 0, then you can see that we would be accepting values of theta, and the values we accept will be exactly generated from the posterior distribution. So that would be perfect. In practice, however, this is going to be impractical, so we're going to have to rely on epsilon, which will be non-zero, and we're also going to have to rely sometimes on summary statistics, which are not sufficient. These are issues which are going to make the pseudo-posterior we use with ABC become more and more different from the true posterior, and so we like it when we can keep S sufficient and epsilon as small as possible. Now, a couple of properties which are good to know about ABC. The first is that as epsilon goes to 0, the approximate posterior is consistent. In other words, it concentrates on the value which was used to generate the data. And another property that's interesting, especially in our case, is that we know that the optimal summary statistic is going to be of the same dimension d as the parameter theta. Now, of course, that doesn't tell us what that statistic is, but it gives us information about it. Now, this I introduced vanilla ABC. It's going to be very inefficient in almost any realistic setting. So there has been a lot of work to improve ABC. Some major modifications to ABC are ABC Metropolis Hastings, which is sometimes called ABC MCMC, but it's really a Metropolis view of ABC, and ABC SMC, which is a sequential version of ABC. So both of these are going to be quite useful, especially in situations, for example, where the prior and the posterior are very different. So simulating directly from the prior predictive would be very inefficient. It's going to be able to take your algorithm into regions of high posterior probability. But neither of these is going to be very efficient as soon as D is quite high. The reason for this is that, well, you're now comparing a summary statistic of dimension D between your simulated data and your observed data, and it's going to be very difficult to come within a small distance epsilon of the true data as soon as D is quite large. So these work well in small dimension and not well in medium to high dimension. Now, the idea of our method, which is called ABC Gibbs, is to use component-wise updates, like you would do in the Gibbs sampler. So, if you look at how this algorithm works, you're going to, at each step, you're going to take the jth component of your parameter theta, and you're going to update only theta j according to the ABC approximation of the conditional distribution of theta j given the data and all the other parameters. Alright, so this is exactly what you would do with a Gibbs sampler, only here, instead of sampling directly from the conditional distribution itself, we're sampling from the ABC approximation of that conditional distribution. Now, what you should note here is that since we are considering each parameter sequentially, that means that we are going to have a threshold epsilon j for each theta j, and we're also going to have different summary statistics for each theta j. Now this is going to be quite interesting because it's going to allow us to use summary statistics which are going to be, well, typically of dimension 1 if theta j is dimension 1. And if we are able to find good summary statistics for each of these components, then we're going to have good approximations at each step. It's also going to be easier to choose smaller values of epsilon, since we are now working in dimension 1 at each step, rather than in dimension, say, 20, and so we can get closer to the observed data. So this is the idea behind the algorithm. We're going to see during this talk that it can work in practice, that it's reasonably straightforward to implement, and that it has some neat theoretical properties. So, like I was saying, at each substep, the summary statistic is of low dimension, so it's going to be easier to be within short distance. It's going to be easier to find good summary statistics. And also note that at each substep, sometimes only part of the data are going to need to be simulated. So if theta j only depends on some data xj, that's the only part you need to re-simulate. Finally, note that some of the conditional distributions might be available analytically, in which case we'll deal with those exactly, like a real Gibbs sampler. So maybe the approximation part will be on a smaller subspace. And a last thing to note is that although I'm going to use the word summary statistic, actually this Sj can now depend on the value of the other parameters. Right? There's nothing preventing us from doing it. If we want to, and if it's useful, we'll take Sj to depend on those other parameters. That might open avenues in cases where there's correlation between the thetas that we understand quite well, or where simply defining a good summary statistic requires knowing some of the other parameters. So it's possible that you can leverage this into useful information so that the algorithm is more efficient. Now, a natural application of any Gibbs sampler, including ABC Gibbs, is a hierarchical setting. So the idea here is that you can have a hyperparameter, alpha, which governs these parameters, which I've called mu1, mu2, mu_n, and then each of these mu_j's is going to generate some part of the data, xj. So here, this means that when you're looking at the distribution of mu_j given everything else, so given the data, all the other mu's and alpha, what actually depends only on a small part of the data and on alpha. And so we might take a summary statistic which depends only on xj. Similarly, in some cases, the conditional distribution of alpha given the mu's is going to be available analytically, which will make it easier. Now, a toy example where we know the true posterior, we can sample from it exactly, while using MCMC, is a normal model. So here we're going to have alpha, which follows some uniform distribution a priori, and then the each mu I is a normal variate centered at alpha, and then for each mu we're going to have 10 observations, which are also normal, centered at that point. So if you want that situation, and you want to do ABC, well, it's quite straightforward to use summary statistics. The summary statistic for mu I is going to be the average of the observations that come from that mu I. And similarly, for alpha, we're going to use the average of the mu's. Now notice that in this case, see, the summary statistic for alpha is not a summary statistic at all. It's not a statistic, since it doesn't depend on x. It depends only on the other parameters. But it's obviously the most natural choice, and there's no issue with using it in a Gibbs setting, whereas it wouldn't be possible to use it in a vanilla ABC setting. Alright, so now if we look at what we get, here you have a comparison. The top two graphs are ABC Gibbs, then you have vanilla ABC and ABC SMC. And you're going to have 10 replicas, which is why you have this kind of shading. And you have the dashed line, which is going to be the true posterior, which is what we would hope to get with epsilon equals 0. Now, as you could see, well, obviously all the ABC approximations have larger variance than the true posterior. That's almost always the case in ABC. But you can see that ABC Gibbs is going to be more peaked at the correct location, so it's giving us a better approximation of the true posterior compared to what ABC vanilla and SMC ABC would do. Now that's because essentially we are able to, this is for the same computing power between all the algorithms, and here for the same computing cost we are able to take the threshold epsilon become lower for ABC Gibbs because we are looking only at one dimension at a time. So because of this we'll get a better approximation. Okay, so this is the idea. Now, I'll give you a couple of theoretical results. Now, the first one is the limiting distribution. It's not clear that there would be a limiting distribution to this algorithm, and so our first theorem is to say that the Markov chain produced by ABC Gibbs converges geometrically to some stationary distribution, which we call nu epsilon, in total variation distance. So this is just as the number of iterations goes to infinity, we do have a stationary distribution. I'm not saying anything about it yet. You can look at the paper for details on the assumptions and for the proof. In particular, you can see you'll see that this theorem applies to compact spaces where you have continuous non-vanishing densities. It would also apply to other spaces. We haven't necessarily looked into much detail about how vague you can make the assumptions, at least under some assumptions, which we can verify on some examples. You have this convergence to a nu epsilon. Okay, now that we have nu epsilon, we can say something interesting about it. Now, since we've defined nu epsilon to be the limiting distribution of our chain, well, we can define nu 0, which would be the limiting distribution of our chain if we were to take all the epsilons equal to 0. Right. Now we can say two things. The first one is what you would hope, which is that nu epsilon goes to nu 0 as our threshold epsilon goes to 0. So this is again in total variation. So we have a convergence of our limiting distributions to this nu 0. But what's interesting is that nu 0 is also it's the same limit as what you would get from vanilla ABC when epsilon for vanilla ABC goes to 0. Okay, so in the epsilon goes to 0 limit, we're going to get the same pseudo-posterior as we would with vanilla ABC, the difference being that we're going to sample from it much more efficiently. And in practice, we're going to be able to get much closer to epsilon equals 0 with ABC Gibbs than what we would with vanilla ABC. So we're actually getting closer to this limit, which was what we would hope for. Now, I should note that that doesn't mean that nu 0 is the true posterior. In particular, if your summary statistics are not sufficient, then nu 0 is different from the true posterior. It would basically correspond to a posterior conditioning on S of x, not on x. Okay, so now that this is established, I'll show you a second, more complicated example. So this is a hierarchical G and K distribution, which is intractable. Now, the G and K distribution, it's a standard example in the ABC literature because it's a distribution which is quite easy to define and to simulate from, but which isn't available analytically. And here we're looking at a hierarchical version of this distribution. So it relies on 4 parameters. You have B, G, and K, which are going to be shared between everyone. And then you have a parameter mu, and so mu is going to come from some distribution depending on our hyperparameter alpha. Okay, so it's a relatively ugly graphical model, but it's quite clear to see how you can simulate from it. You choose an alpha, a B, a G, and a K. From that you get the mu I. From the mu I you get the xi, and that's it. Okay. I should note that it's not at all clear that there exist good approximations of the G and K distribution. So in the one-dimensional case, sometimes you can hope to get an approximate MCMC scheme. It's not at all clear how you would do it in this situation. And so it's quite natural to rely on ABC. And it's also quite clear that this is going to be difficult for vanilla ABC because of the large number of parameters. Here, you have basically n plus 4 parameters, and we're going to take n equals 20. Alright, so interactable likelihood, so ABC methods are natural. Attaining a small epsilon is going to be hard for vanilla ABC, and as you'll see in a minute, what's usually going to happen for vanilla ABC is that it's going to end up with epsilon which has to be very large for you to get a decent sized sample, and so that means that you're basically sampling from the prior. Now ABC SMC is going to have a different issue, which is going to degenerate, and so you'll end up with approximations of the posterior which are completely worthless in this case. It's quite obvious that you couldn't use them, and again, that's a dimension issue. Okay, so here on this graph, you're going to see the 3 methods, so ABC Gibbs, ABC SMC, and vanilla ABC. In this case, you have a red line, which is the true value used to generate the observations. So that's what we would hope to recover. And you get to have the 4 line, which is ABC Gibbs. And then you have the dashed line, which is ABC SMC, and the so you have the little dashes, which is ABC SMC, and the big dashes, which is vanilla ABC. Now, if we look at this, so for alpha, ABC Gibbs and vanilla ABC are both doing fine. They have a posterior which is centered on the true value. ABC SMC is quite peaked, and it's in the wrong location. And for all the other parameters, what you can see is that ABC Gibbs is centered on the correct value, usually quite with small variance. Vanilla ABC is going to basically give you the prior. It's going to be a very vague distribution. And ABC SMC is almost always peaked in the wrong place. All right? This is because you have particle degeneracy. So your SMC sampler gets stuck somewhere. It can never escape because it can't manage to get close to the true data. The reason why ABC Gibbs manages, once again, is because it's only considering one parameter at a time and actually part of the data at a time, which makes it much easier to get a match between the simulations and the observations. Okay, so you can have a couple more examples and further theoretical results in the paper. I'll just say as a conclusion that this is a rather powerful tool for intractable graphical models in medium to high dimensions. And what's nice about it is that it's quite straightforward to implement. Now, anybody who's tried to implement an ABC SMC from scratch, the first time you do it, it's quite painful. You have a lot of tuning, it's not at all obvious how to do it. Here, ABC Gibbs, well, it's very close to a Gibbs sampler. It's quite straightforward to implement. It does raise questions about the optimal choice of summary statistics so these lower dimension summary statistics. How can you choose them optimally if you don't have expert knowledge? We'd also like to extend the theoretical results on asymptotics to larger classes of models. Now, one last thing I'd like to say is that the ideas and the proofs used in this paper could be adapted for componentized versions of other approximate schemes. So here it's ABC Gibbs, but you could use the same ideas to have Gibbs versions of whether synthetic likelihood or VB or whatever your favorite approximation is. You can probably adapt some of the ideas, and you can adapt some of the proofs. The proofs in this paper rely on couplings between the Gibbs version and the standard version, and you can probably adapt this for Markov chains for other approximations. Okay, so the paper is on arXiv, and we're hoping it will be published quite soon. And you can also find the code on GitHub to reproduce all of the figures and all of the examples. Thanks a lot.